So as we recap, what we really did was we took some hot water, we mixed it with some cold water, and we wanted to see what happened. So you guys did 5 trials of that, and you were using different volumes each time. So for those of you guys at home, this is just a general idea. You're not going to actually do this lab. You'll be exempt. But this is the basic idea. So this first trial, we took 50 milliliters of hot. We took 50 milliliters of cold. We mixed them together, and we measured the temperature of the hot and the cold separately, but also the measure of the mixed. And so let's go through some of these questions. What happened to the temperatures when you mix the hot and the cold? What do they generally do in the mixed? Yeah. Oh, go ahead. Go ahead. Sure.
Would you answer?
They like kind of mixed, like averaged in the middle.
Yeah, they averaged in the middle, or they met in the middle. I think that's what most of you guys saw, is that they kind of averaged out. Okay, they sort of met in the middle. So if you had 20 degrees and 40 degrees, they would usually hover around 30 degrees once you got them all mixed, something like that. Did this surprise you? Well, that will vary. Some of you guys will be like, yeah, I was actually kind of surprised by that. Other folks will be like, no, that's what I thought would happen. There's no right or wrong answer there. It won't be like, nope, didn't surprise me. I'll be like, what? Like, maybe you're not surprised. I don't know. That was just more of a reflection question. Now, what kind of amounts did people use? Jada, what kind of numbers, what were some of the volumes you guys used? Just the volumes. Uh-huh. Mm-hmm. No, I mean, what volumes? What are some of the milliliters you guys picked? That's the number you guys got to pick.
We chose basically everything but 50.
Everything but 50? So what were some of the ones?
Started at 40 and then ended at 90.
Okay, so you got like 40, 60, 70, 80, something like that. Did anyone use anything above 90? Anyone use 100?
Yeah.
Did anyone use anything below 50? Anyone use like 30 or something?
We did 30.
Okay, good amount of folks, okay. So you guys used pretty much anything between 20 and 100, which is what I was hoping we would kind of see. Did anyone see anything different than the temperatures basically meet in the middle?
Uh-huh. I feel like the more, the amount of water that she used, since we like added on, like we would do like 50, and then we take the temperature, but we wouldn't pour our water out, we just pour more in there, and I feel like that kind of changed it because like the water would have more time to get like warmer.
Okay.
Does that make sense?
Yeah, so that does make sense, and that we can actually touch back on that in question number 7, possible air issues in this lab, because sometimes if you don't take the temperature right away, it can change on you. So that's a good idea. Generally what we saw, even though you guys use like 20, 30, blah, 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 100 milliliters, we saw that it didn't really make a difference. They still kept meeting in the middle for the most part. They still kept meeting in the middle, which is pretty good. It's pretty much what we were expecting. Hey, what is it about styrofoam cups? Why do I want you guys to even use those, Skylar?
Glass takes longer to absorb heat, and styrofoam is much more easier.
Okay. Demetrius, you want to add to that?
Because if hot and cold go together in glass, it'll break you.
Oh, okay. So you're worried a little bit about heat shock potentially. That's always good to worry about that. It's probably not too much of a temperature change, but I'm glad you're kind of thinking that way. AJ, get you next Trinity.
The styrofoam is a better insulant, so when you're kind of like holding it around, it changes less with the ambient air than it would if it was in a beaker.
Okay, yeah, so we're dropping the term insulator there. Is that what you're going to kind of go with?
He said, but he do like Bill Nye the Science Guy.
Bill Nye the Science Guy. Joe, do you want to add anything to that?
This is like kind of a guess, but like the table wouldn't absorb the heat because it wouldn't have like gone through the styrofoam.
Oh, okay. So you're like, all right, so the styrofoam sort of prevents the heat from kind of going through it. Yeah. So this is a term that you've probably heard at least before, but you haven't really talked about in class, and we're going to talk about this a lot this week. The idea is that styrofoam is an insulator, okay? Styrofoam is an insulator, so it really slows down the change of temperature. So the temperature won't change. It won't get too, it won't go up or down very quickly if you're in a styrofoam cup. That's why we doubled it up to really double that insulation. The point is, like, these styrofoam cups really slow down the transfer of temperature. Now, which sample gained energy? Well, that was the cold water. The cold water gained energy, and what was the number that you saw that let you know the cold water was gaining energy? What changed about the cold water when you mix them together? Yeah?
Okay, so the thing is like the heat, like, so the hot water is like heating up the cold water.
Yeah.
It's like transferring. Like, you know, like when you leave ice cream out, it gets warmer, obviously. But
That's true.
Mashed potatoes out, they get colder.
Yeah, so the temperature went up for the cold water, whereas the hot water is the opposite. The hot water's temperature went down. Okay? So that's where we're sort of seeing or meeting in the middle. Now let's talk about this chart at the end here. Now, there's a couple things I want you guys to note and write down. So we have like 2 sentences of notes here. Here's the first one. So this is at the bottom of your little handout. This little triangle, it's the Greek letter delta. and it means change. Okay? It means change. So if you ever see something like this, delta T, that means a change in temperature of something. Okay? So it's like, how much did the temperature change? That's one thing you guys need to know. Now the next thing I'm going to show you has a couple of numbers. Please don't write down the numbers. I'll tell you the thing you want to write down towards the end, okay? So in my lab, again, please don't write down these numbers. My hot was 58 degrees Celsius, and it went down to 40 degrees. So we're like, oh, delta thought. That's the delta T of the hot, okay? The change in temperature of the hot. So my hot changed 18 degrees. My cold was down low at 22, and it went up to 40. That delta T, that change in temperature, was also 18 degrees. So we were hoping if you had perfect data, which some of you guys were probably close, your two difference columns should have been close to the same number. So I know that Emily had a trial, like I think her third one was pretty close, where these two numbers were almost exactly the same. Your trial number 3, I think. Now, so we saw that the delta T of hot was about the same as the delta T of cold. And here's the big idea. Here's the thing you got to write down. You want to box it up, highlight, put stars around. It's the point of the lab. The energy lost by the hot. The energy lost by the hot. And the energy gained by the cold. So the cold went up in energy, the hot went down. Should always be equal. Energy lost is always equal to energy gained. Energy lost is always equal to energy gained. That's the big thing you got to write down. That is the point of this lab. This is a key idea, maybe the biggest idea of all Unit 3. If anything ever loses energy, that energy doesn't disappear. It's that exact amount of energy is gained by something else, and vice versa. So the energy gained is equal to the energy lost. All right, and that's a wrap for today. If you are absent today, you don't have to make up this lab, but just know that the energy gained equals the energy lost. See you next time.